Hello, Jennifer. Can you hear me? Can't tell if it's working or not, but we'll go ahead and get started. We have this is right actually. See, another time soon. So first, I want to thank you for your journal stuff that most of you sent in last week. I know it was a lot of work to do that sort of searching. Some of you still clearly need to work in your process. It's taking longer than it should. And it's important to not just try and catch up on time by saying, I just read the titles. I guarantee you there are lots of good papers whose titles are not at all descriptive. We'll talk about why you might want your title to not be descriptive. That's later when we get to writing. But, so going through the browsing process. When we get to our other part of our assignment for your next assignment, right, there will be some of this. I will not force you to go browse a particular location, but I still recommend it. Right? There's a lot of things. Now, how many of you found papers that you did not expect when you were doing your browsing? Something interesting? I didn't. So, and I know Keith, who's actually not here today, is literally on a plane. He commented in his that like, he has a better understanding. If you are in whatever subfield you're in, you go look at the biggest conference, a couple of your journals. Right? If you go look at the biggest conference in your field, there's probably more there than you want to read in the entire year in terms of actual reading. So you've got to find a way to browse through and find what's important. And long term for your career, as I said last class, for me, the best predictor of how well students are going to do as a PhD student is how much they are out there reading. Now, I think that doesn't mean you read all the papers, but you've got to find the ones that are relevant. I continually push my own PhD students where I know there's an important paper, and I will not tell them. I will just keep asking them enough questions until they finally go find the paper. Because they got to learn how to do that on their own, right? I already know how to find papers. I know what papers are out there. Now, they should come to me and say, here's an interesting paper. We should discuss it, not the other way around. Right? So it is your responsibility as a student to be driving the research agenda for your research. You should listen to what your advisor says. If he or she says, go read this, you should go read it. But that shouldn't be the only stuff you read. You should be out there looking for something new to go to them and say, see, I found a good paper. We should talk about this one. Once you start doing that, you're approaching the point where you don't need your advisor anymore. You're not ready to graduate until you don't need your advisor anymore. Right? So you've got to make that transition happen. So, and based on the hands last time, not everyone here knows Git. And I found this out last semester. I sort of went through it. I had a lecture on it last, but I didn't do any homework assignments on it. And by the end of the semester, I learned there were people that should have been forced to do homework exercises in Git. So I'm going to make sure by having you do some Git assignments today. So if you've already known Git, I apologize. This may be a little bit boring, but so let's talk about Git. So Git is a tool, is a form of versioning system. Older versions, people have used things before, CDS, source safe. These are also versioning systems. Git is a much more efficient versioning system. It's what underlies all of what we do in the Linux kernel and whatever. So a couple of key files that you'll have to deal with. So inside your system, inside your home directory is something called tildes in the home directory, which is tilde/.git config. This is where a bunch of your configuration parameters are. Sometimes Git will behave in ways you don't understand because you save some Git parameter and it shows up in your Git config. You can always go look there for a bunch of stuff. In any top level of a repository, so Git, and I'll go through more about what repositories are, there's something called .git. It's the top level directory, and it contains all of the objects and stuff that Git actually uses. Inside of the Git directory is another .git/config, as opposed to no slash here. And this has a project-specific configuration. This can be useful when you're trying to figure out why is Git doing something, where is Git, what's the original repo and stuff. Oddly enough, once you have a directory that you got from somebody else, you want to know where it came from, you look in your .config file inside the directory, you'll find out where was the URL was coming from in its history and stuff. There's another file called .gitignore, which is stored in the directory. If you want to ignore an entire directory, because I don't want to have that backed up, then I can put a .gitignore in the directory and just ignore the entire subdirectory. I can also have gitignore particular files or particular wildcard, so I can ignore everything that ends in tilde or everything that ends in .exe. I don't want to store my binaries in Git. So I can put that in my Git config and add items to make it go away. So some things about Git. Git has some real advantages in terms of its resilience compared to, say, CVS. CVS had a single repository, and then people had copies of it. But there was a central repository. In Git, no one repository is actually a whole lot more special than another. Right? I can clone from one, I can push things back up and forth. It's a truly distributed architecture, which makes it very resilient if you don't depend on one machine being down. You can set up to have multiple seeds, and then you can get it from any one of 5 or 6 different places. Those places are automatically kept up to date. So Git is very powerful when you're using it for things like mirroring because it has all these nice properties. Speed, it's very fast compared to things like source safe, CSV, Subversion, all of it. Sometimes literally an order of magnitude faster when you're dealing with lots of files. So it was designed to be very fast and very efficient. So the compression can be done across repositories and not just per file. So one of the things that CBS did is it would allow you to have, like, it would look at deltas, differences between files, but it would do it per file. In CBS, in Git, it actually does it across the entire repository. So if you have 8 files, they're almost exactly the same with small variations. Some programmers like to do where they keep versions. Git will say, well, they're all variations of the same core file. It has just the differences between them. Where CSV as a version would actually have per file deltas. It minimizes the local size as well as the push and pull transfer. So this allows it to compact things and store things in a very, very efficient way. The object model is simple, which we'll also come back to. Is one of the systems is sometimes Google. And has a large user base with robust tools. As I said, this underlies all of the Linux kernel, which has been distributed for a long time. But now with things like GitHub and Bitbucket, like people are using it for a very wide range of things. And so literally companies will often want to see your GitHub profile when you are looking for a job. So my recommendation is have a GitHub profile. As a student, in fact, I think now GitHub has private repositories for everybody along the sites. But as students, you can have unlimited number of private repositories. We can set you up for that. GitHub now tracks your activities on projects, both yours and other people's, even if they're private. So the employer can see you've made 500 Git commits. That says you're an active software developer. If they look at you, you've had 7 software commits, you're not much of a software developer because you're not using the tools they think you should be using, at least depending on the company. You could be using other tools, right? Yeah. Right. Yeah, but it's annoying, unfortunately, how many of them. So actually, we were using Bitbucket because it was free for private stuff for a long time. We switched to Git because I got feedback from students who were graduating. Like companies asked them and said, well, your Git profile doesn't show much. It's like, if recruiters are looking at it, then, and part of this from an education institution, yes, you can use all these other things, but you can do them on Git and do something on Git. 7 is really few, or none, right? 500 is a lot, but having 30 or 40. You just do Git for just your papers, your private repo that shows lots of activities, and all of a sudden you look like you're a serious software developer. You touch no code, you just laugh. We'll talk about that today. So some disadvantages. Git definitely has a learning curve, especially those who use to centralized systems where you have the unfortunate unlearning curve, because Git does not work like these other systems. So you have to unlearn some of your previous behavior. There's definitely a lot to learn, some of the conceptual differences which have to go through, and there's a huge amount of commands. So I can't remember them all, right? That's what man pages and Google are for, right? So I know the basic operations, and if I want to look something up, I can just do man and find out the commands. So let's talk a little bit about a high level of what Git is. So Git uses an idea of what's called snapshot storage. It's a logical view. It does actually use deltas, differences between files and packs, but because they're not per file, they're a lot more complicated. So it's best to just think of it in terms of its snapshot. So in traditional things, traditional version control like CVS or whatever, we think about having a file at some point in time. So here's I created everything. Then I'd have a change between this file and the next file at time 2, and then some at time 4, I could have another delta. And I kept track of what were the changes in the file. The whole idea with deltas, of course, was to reduce how much I have to store. In Git, the idea of a snapshot is at any point in time, I have a snapshot of every file. Those files may or may not have changed, but what I see, of course, is just all the files. And because it computes its deltas, when nothing changes, this file doesn't actually change. It's there. But the delta compression is across all the files, so it's more complicated than what that's going to look like. So some very basic Git functions. So let's say I create a file by saying hello, echo hello into a file, so it's a standard command. I can now say git diff. Now, I haven't actually shown you how to make a repo in a second, but assume I already had a repo. It would show the changes we've made to the repo. If I say git status, it shows the list of modified files. If I say git add hello.txt, this is now going to take the file called hello.txt and say, add this to the repo. At this point, when I said status, it actually would have said I had a file hello.txt that was not stored in the repo. It's in the directory. The repo doesn't actually have things in it until I explicitly add them. Once they've been added, all changes to that file will be tracked. But by default, files are not added. You have to add them by hand. And then if I did diff again, it would show no changes. If I do git diff head, so if I go back to, oh, actually, this is the next slide. And by the way, if you type all these commands in Git, you can sort of play with all this. So I can do the head, and then I can do a second commit. I can make some changes. So when I added a file, it basically marks the file as something that should be added to the repo. It doesn't actually add it yet. Everything in Git is a sequence of operations of set stuff up and then do what we call a commit. This line here, git commit -m second commit. So this is a comment. This is the marker I want to put in with it, and this is the command. Until that time, Git just queued up all the changes you want to make, and then when you say commit, it goes ahead and makes it. Now, the reason to separate adding what I want and then doing the commit is, in fact, not only can I have added files, I can have edited files and whatever, and Git doesn't go to check the differences between what you have and the remote repo does until you ask it to do the commit. In fact, oddly enough, commit may not commit things. It's actually the intent to commit. Because if it goes to commit and it says, oh, look, the other side has changed while you weren't watching, then it'll tell you you have to pull and merge first. Because it says, I changed the file and you changed the file, now who wins? Well, if this person's already pushed their commit, then you're going to be told you have a conflict. You'll have to do the work to merge the two files together and then push those results. So the basic idea, at any point in time inside of Git, we have what's called the head. This is as a named command, it's actually a place. The head is the last commit snapshot, right? It's really what's going to be the next parent. So the head is what has already been committed by everybody else. Now, when I go to do my operation, I'm going to have my index. The things I added are what are the proposed next commit snapshots. So I've made changes to 15 files and I've added 3 new files. All of those will be what's in the index, okay? And those are the changes. The files that are currently in my directory that didn't get changed aren't in the index. They're just in the working directory, which is my sort of sandbox where all the files are. So this allows me to do lots of local things, take them, and then when I go to play with them, when I do the commit, it's going to commit the files. It's going to go back up to the head, and if the commit is successful, a new head will be created. And before that, everything is just in the index through what are called staged files. So the basic workflow, so somehow I have to create a repo with a command to initialize it, or clone one, which I will show you in just a little bit. You do some edit, you edit your files, you stage the changes, which is I'm ready to make them, review your changes, commit your changes. That's if everything goes well. If you get yelled at during your commit that there's some other changes, then you will have to pull the old changes, merge them, and we'll go through an example that does that as well. So how do I initialize? Well, the commit is real simple. Git init. That makes a new repo. It says initializing empty directory. It depends. So this is I did it in a directory I had already called git test, so it's going to add that as a repo. And then if I do ls-l of the .git, you'll see all the files that are inside of it. So it's got a file. Oh, I should use my mouse pointer so it shows up in the videos. So I've got the head, which is a small file. It's only 23 bytes, but it's really just a hash. Basically, all the names and indices in Git are just hashes. So it's keep track of stuff. And then it has, of course, the thing I mentioned. The config is in there. description, which is when I created it. I could have put in the Git init a direction, a comment. I didn't. And then info, objects, and rest, which are the parts that go together to make the repo. So as I do my basic operations, I can edit files. Okay, so I might go into my editor and do something. So in this case, I'm going to use whatever editor you want. Most of a number of more advanced editors: Visual Studio, Eclipse, VS Code, Atom, Emacs Vim, Sublime, and Notepad. Pretty far down the list. Notepad++. All of these have direct interfaces for Git. There are commands you can add for Notepad++. Is pretty hard, but for Visual Studio, Eclipse, VS Code, Atom, Vim, Emacs, right? There are modes for interacting with Git. So they know what to do. And I sometimes forget what's the next command because the command in Emacs, which is my editor, for almost everything in dealing with Git is do the next logical thing. And so it's like it's a sequence. So whatever state I'm at, it knows what the next logical thing is. So I don't have to remember, do I need to push, pull, commit, add, or whatever. It just knows what's the next state given what I'm trying to do. But most of them have very explicit, I mean, Emacs has explicit commands as well. So if I go to do something, so as I said here, I initialized the init. So echo is probably an even simpler editor. I just like echoed some file. So here's the command git status, which I showed you. It shows me where I'm in. I'm on branch master, initial commit. So untracked files, and it's telling me that this file hello.txt is not yet tracked. Git doesn't, it sees it's in my directory, but it doesn't actually know what to do with it. So, and it says nothing added to commit, but untracked files are present. So Git's trying to tell me that if I do this, I have not saved a copy of my local file. So that's when I do the command git add, which I showed you before. So I do git add hello.txt. Now when I show git status, it's going to show me my initial commit changes to be committed. So it's showing me what's going to happen. I'm using that. I should use this. So it actually it tells me here how to remove something before I've even added to the repo. Like if I accidentally did this, most commonly happens when people say something like git add star, right? And you look and it added a whole bunch of garbage files. You don't want to do those. So then I can do git rm minus cached in the file name, which John says. So now it's telling me to enter the new file. So very straightforward. Any questions so far? I know it's pretty boring. So so now I can commit this. I can do git commit minus am in my message. It's going to show me the message. That's the one to add to it. One file change, one insertion, and it created this new file within the Git repo. Those are the basic situations. I'm in some working directory. I add it. It shows up in the index. I commit it, and it shows up in the repository. Now, if I want to show the differences, again, the command I showed you before, git diff, it's going to show me the difference between the working directory and what is staged. So if I went back here, I could actually do, or this actually just git logs. It would, in this case, because the files hadn't changed, it wouldn't show me much of anything. And git diff minus cache will show me the difference between what was staged and the current head. So the repo has a head, that's what's stored by everyone else's copy. And I can now see the difference between what I have and what's stored with the cache, or between the working directory and what is ready to be go. So after I did the git add command, it staged the file ready to go up. It's not actually up there yet, but I can edit the file again after that and see other changes, and Git will allow me to do that. So the other thing I can do is I can view the history. So I can do git log, and it will show me all the changes. So here, this is just doing the same thing. Hello, whatever. Here's the git log. And then it's going to show me, and there's this long hex string. This hex string is the name of that commit. That's the hash, literally the hash of the file that we're in. So it's showing me who made the change, the date of the change, and a comment that went along with it. And then it's showing me over here a second thing. So this actually took the file hello text and changed the file to have the content hello too. So I overwrote a file with new content. And then I committed that. Right? And in the log, I can't see the changes. I just see the comments. Okay. Why do you think it doesn't show me all the changes in the log? Why not show me like this what files were changed, or everything else that was changed. Well, this simple example, that would actually probably be okay, but in practice, right, I might have changed dozens or hundreds of files. And it's just too annoying to put all that information in the log. So given any particular command, although here I said git diff cached, I can actually say git diff, and then I can put this hex number in, the actual hash of the thing. And it'll show me the difference between where I am and that commit. I can actually do the difference between any pair of commits by saying get diff and a pair of heads, and it'll show me those two different. So if things go badly, if I need to go back to a previous version, and I want to be careful as I phrase that, I can switch back to using an older version. Git does not delete stuff unless you're really aggressive. Back to that. So it's very hard to lose stuff with Git. So if I do git checkout, and now here I'm going to be lazy. So one of those two branches, yeah, this one here, commit FF07, FF0F7, whatever. Right? That's a really long string. That'd be really annoying to type. But Git is actually smart enough that if I give it a substring, the first 4 characters are unique enough, then it'll say, fine, I'll just use that. I know what you meant. I don't need to have a whole string. So git checkout will make a new branch. The idea here is I had one branch of code going. I can make a new branch to make changes in. And now in this new branch, I've gone back to the first version. Notice this version with the FF is when I had just the original hello in it. So now when I check that out, if I look at the content of the file, it's back to the original version. I can now modify the file again. I can commit. So git commit minus AM, commit on branch. And now when I look at the file, I've added the word branch to it, right? And now I can check out FF00, that's the one I had here, and it's going to yell at me. It's going to say I'm in the detached head state. I can look around, make experimental changes, whatever, but you can disregard any commits you make at this state without impacting any branches. So I can make a bunch of changes temporarily, test stuff out. And this is why Git is so powerful from a coding point of view. Because they basically set it up, go run some temporary experiment. Before I push everything back in this new weird state, I can run an evaluation, test everything, give it a test out, okay, then I can decide if I want to do it. But if not, I can go back. So if I want to create a new branch, or to retain the commits I create, after I've done this, I can now do the checkout minus B with a name, right, which is what I did up here. So in this, I checked back out the old version. So the stuff I checked out here in this new branch is now gone. When I look at the file, I'm seeing the old version. I can switch back to that branch by just saying git checkout minus B. I'll be over there. So I can have 10 or 15 versions of the code. This is really important because I see lots of PhD students whose approach to coding isn't maybe what it should be from a software engineering point of view. They don't put all the parameters on the command line. It's research code. You don't know what you're going to need until you're in the middle of it, so you're doing it, right? And then they like put comments in and they say 15 versions of a file, and it gets really messy really quick to remember, really quickly. And because you can't remember 6 months later what each file was for, right? Much better to do something like this where you use Git, and instead of viewing this as I just tack something on the end, right? I can have a version of the file, and I can name my branches, and I put comments in about what each one was. And people are like, oh, I don't want to have a copy of my code. It's too expensive. Don't have a copy of your code. That's what Git's for. If I change one line, the Git repo will increase by like 60 bytes. Right? It's nothing for you to have these extra copies laying around. Very, very cheap. So as you're doing your experiments, and I'm going to watch it in this class, right, to start using Git, but more we'll talk about it for your next assignment. You should think of it as check your code, you can do this commit in branches and whatever, and Git very, very frequently. So when I'm coding from a company point of view, my engineers, right, I would expect something between 50 and 100 commits a day. If I wasn't seeing that in the Git log, if I wasn't seeing like 40 or 50 commits a day, I would have a chat with them because it says they're not actually using Git the way they should. They're thinking of Git as I should wait until it works. That is not how you should use Git. If I have a reason to make a change, I should document that, commit it to Git, and then run the experiments to evaluate it. Not run the experiments to evaluate it and then commit it. Right? you do it in the other order. Because this way you can go back and look through, here's why I made that change, here's why I made that change. If it doesn't work, that's okay, document that as well. But you want to be making all those commits. They're very cheap and allows you to keep a good history of what's going on. So if you accidentally do something and you're not happy with it, so I can check out a specific version of the branch tree. This is also important from a real production software point of view, but even from a research point of view. If we've released version 1.35 of our code, and we're now at 1.6, we're doing stuff internally, well, we have a bug fix to 1.35, I can check out that whole tree as though it was back there, make the bug fix, and push it. This is why the trees become important, because I release some code. I'm now down here doing new experiments. I want to go back and fix this. That actually makes a new version of this code, right? And there's this idea of a growing tree. So I can reset my current working tree. I can reset the current version of the tree to a specific version. And if my current directory, I've been doing like testing, I have a bunch of random stuff, changes I've made, and I really want to throw them away, Git won't. It will yell at you. If I want to be aggressive, I have to tell it -4. So Git reset -4 will say, take all the changes I made locally and throw them away. Generally, I rarely use that command. I don't really recommend that command because Git has other ways of doing that. There's another command called Git stash, which for some reason is not on my list here, but it's one I use all the time, which will basically think of it as like a little cache. It will take my current version, stash it away, not name it, go to some other version, and then I can come back to it by revert. So Git reverts a commit, does not delete the committed object. It just applies a patch. Right? So this is, again, from a conceptual point of view, if you're doing subversion or whatever, here I'm not going to really throw away everything. It's just a different name. Switch back to the old version. The new version is there and is a patch, so I can revert and go back to where I was. So Git never deletes a committed object. Once you've committed it, it's there. It's really hard to shoot yourself in the foot. It's there someplace, right? In my company, once or twice we had people really do bad things with Git. The most common of which was remove stuff. Right? Now, when you do the command git remove, that does not remove stuff. It actually just marks it as deleted, but it's still there. So trying to save space, some of my engineers try this command like rm on the command line. Right? Actually, it's because it's git rm. You forget that and you just do rm, you're okay. But if you do rm of the prime Git repo and no one else has a copy, that's the only way to really hurt yourself. So we basically didn't want you to use a rm command too often, but at the command line because it's dangerous. Everything else is pretty easy. So branching in Git is lightweight. In CVS or Subversion or SourceSafe, those tools, when you do a branch, it's like a copy. Because it does per file deltas, it can't keep track of things differently. Git branching is literally just like adding a tag to the file. If everything else is the same, your branch is no different. It's exactly the same with one line in the logs. If you change one file, that's the only difference that's there. So the branching is really, really cheap. That's why I said you should just create lots of branches as you're doing your research. Right? You're always on a branch. There's a branch called main, and then every other branch you make is just some main version of keeping track of it. Git has a whole bunch of tools for merging with branches and making these changes easily. Branches can either be local or remote. So although we'll talk about this a lot more later with the remote repositories, we'll show you what that means, but I can have a branch locally that is not in the primary repo. In fact, from a developer point of view, that was very common. You would try 8 or 10 different things locally, committing them all, but only pushing to the repo once or twice a day, when those commits are actually validated. So that was, from a software development point of view, that was the thing I tried to get my engineers to really understand. Commits are local copies, so I can keep track of what's going on, and I can see a log of everything that's happened. And then when I push it, that's when it's stored in somebody else's version. So I can have 50 branches and do 100 commits locally and not impact anybody else's work, but I have all those different versions I worked on. And then when I do a push, think of that as literally pushing it up the hill to somebody else's server so it's there. Okay. For some key commands for working with branches, I can say git branch and make a new one, or git merge 2 branches, merge as 2 functions, but it'll allow me to take 2 branches, merge them back together. So I was describing it before as a tree. Well, eventually I might want to actually bring it back into a graph and have the 2 parents, 2 things have parents, right? Bob makes a version, Joe makes a version, they do some work together, and then I want to unify them back before we make a release to the customer, so I can use the command git merge to take those two pieces together. And if I want to, Git has a command called git cherry pick, which allows you to choose specific, and I can actually edit them. So I can now say, well, I want this file from Bob, this file from Joe, and they're going to merge them. Don't actually try and merge the files separately because they're going to conflict. And I like Joe's version better than Bob's, so it's not like a line-by-line merge. It's Bob's file, Joe's file, and we put them all together. So I can just check out a particular branch, and I can pick out branches within branches, right? So developing branch, another branch. If I just do the command git branch, it lists all the local branches available, so I can see all the possible branches from where I am right now. And then I can go back to the merge and cherry pick. I'll show you some examples to work through this, right? So Git sees a commit in terms of where we are, branches and the take commits that we're working on. So really, that's why they're so lightweight, right? So a commit is, here's a tree or a graph that I'm going to put back in. And when I call it a branch, it's just going to put a label in here. So if this is where the current structure is, right, I can go in and then say, okay, let's create this branch C1. If I tell it to make a new branch called experiment, right, and I say now the command git branch, it's going to show me with a star the branch I'm on and the fact that there's a new branch. And this is, by the way, is one of the things that is confusing for many people. I just gave the command git branch experiment. Git does not change to that branch. It just makes the branch. It doesn't actually commit to it, right? And that caused lots of confusion when people get started because you think I made it, I should be on it. No. Your default is you stay wherever you're at. You actually have to check out experiment to check out that branch. Now I'm on that branch. So I can do some experiment, do some stuff, and then I can do a git commit, and now I will have a new branch committed. So now I have 3 different snapshots. Okay, this one is named experiment, right? Because it's got this name out here. This is the default branch. I can do some more work on this same branch, and then do another commit. So I can run an experiment, edit the code, do whatever. Then I can do get checkout default. Default is the name of the first branch, so it's back to there. Do some code editing on this branch, right? So if I've got different experiments where I have different parameters stored in my code or different, a couple lines of code difference, right? Now I want to go back and I want to change the main branch where I actually have the core of my code. I go do that, right? And then of course I can commit that, right? Then I can check out the experiment again, go change some of that code, commit it, and now I have this branch, right? Now notice, depending on how the files that I changed here, if those files were inherited, this entire branch has changed, right? But it didn't change, right? So I changed some course files, right? So now how do I make these two come back together? Because if I wanted this change to affect this code, and if they're in any of the same files, then it's not going to see these changes. So I can now do git merge, force them to do that. So the steps to merging is 2 parts. So I want to check out the branch I want to merge onto. Right? So if I wanted to merge onto, so here, right? If I want to take all these changes and merge them back into that branch, then I want to merge from experiment onto default. So I want to then check out default. Okay. And now I want to take git merge experiment, which takes the experimental stuff and merges it into that. Now, why do you think it matters if I'm merging? Which one do I want to merge onto versus the one I'm merging from? What kind of differences do you think that makes? So one, it'll keep the repository name. After it gets done, the name will be default. Okay. Why else might I care? So when it looks at the differences between these 2 files, right? So if I'm merging on top of something, I'm going to say new things go on top of this, right? And this really just has to do with the way conflicts are going to be resolved. Which one is given the default behavior, right? So when I merge two files, and the files have nothing in common, no overlap, then they'll just merge it. But if the files have a conflict, there's a default of what it'll try and do to satisfy the conflict. And it unfortunately is environment specific how you handle the merge conflict. So if I'm doing it in in Visual Studio, right, it'll actually show me, and the defaults will be the ones that if I just hit return are the ones it will take. If I do it in Vim, Vim does not have a default forced insertion. It makes you choose one. So it depends on what editor you use. So there's a small variation in that as well. So after I've done that, right, I can now check out experiment. And if I check out experiment and make a change, how will this graph change? Say I'm going to check out experiment. I'm now going to change some code and put it back in the system. What part of this graph will change? Right, so here, C5, which is the head of the experimental branch, even though I did a merge with experiment, when I make a change, it comes off of here. So I'm continuing expanding this, not the merge version. This is the other reason why merge from and onto become important, because default branch will now grow. Default branch will grow this way, but the experiment branch grows over here. So the one I merged onto is the one that, when it's growing, will have all the changes. Experiment doesn't see any of that merge effect. Okay, so if I now check out default, right, and I can merge with experiment again, merge with experiment again, right, now it makes a new head and puts the experiment stuff, the new experimental stuff back into it. So why is this so cool and why is this very, very useful? In the beginning, it's a little bit confusing, but I do think it's worth your time to get through this because you'll all be doing complex experiments, hopefully, part of your thesis. So this allows us to really do nonlinear development. So I can be working on a code that's in production. This is your prime experiment or whatever. I can create a branch for some issue, some idea I have, work for 10 minutes. Someone asks for you to go do something else, right? You want to change this other experiment. You want to have 4 or 5 ideas running at the same time. You can check out that, you create a branch, you fix the issue, you check out this, you merge the two, and you can put things together, right? So this is just a pure software production point of view. But the same ideas will show up in your experiments. You'll probably not want to linearly follow one idea at a time, because if your experiments take any time to run, you don't want to be waiting for one experiment to finish before you work on your next ideas. So if you can build up your skills with Git and have 3 or 4, that one's running, this one's developing, right? I get very annoyed when my students say, well, I will do that as soon as this experiment's done running. It's like, well, while that one's running, you can be working on the code and testing out the code for the next experiment. You don't have to wait for that experiment to finish to do that. And that becomes pretty important. Now, just like we named branches, it's sometimes useful to take shortcuts to make it easy to remember everything, right? So branches can be made from any commit, and I can then make a name like release version 1. Right? Now, why would I want to have a name for it, given that I already have named branches? Why would I want to tag release version 1? Experiment, proposal experiment. Why would I want 2 different sets of names? Oh, but I already have a name for the branch, right? So why 2 names might be more confusing. Right? Well, the reason is that as I work, the experimental branch or the default branch is going to keep advancing. What I really want to do, and the whole point of a tag, is to tag a snapshot in time. Release 1 is the code I released in public. Now we're going to keep developing. I always want to be able to go back to release 1, and it's not one file, it's like every file. So the branch names keep advancing as the branch advances. I don't want to kill that branch and only make new branches, so a tag lets me do this, right? So again, this can be useful as you're working through your thesis to sort of tag, this is the experiment from chapter 2. Right? This is all of the code as it was at that point in time. Then I can keep working on the code, right? And I don't have to worry about like copying zip files with source code, right? I had some students who still do that, right? That's not how you want to do it. Put it in here and give it a nice tag name. So another thing that Git can do that's pretty powerful is dealing with what are called submodules. If your software has dependencies, and those dependencies are also held in Git repositories, you can basically link the two of them together, and I'll show you an example in just a second, so you can make information about how this works in your program. So if I want to initialize a submodule, I can say git submodule add, and then a second git repo. This creates a directory called project, because I call this one project that I'm linking to, right? Inside your directory, I can do cd project git checkout and some new version, and you'll get the exact version you wish to use. This becomes important when you start building in other people's libraries, because your code may depend on version 1.3 pies hit. And the next thing you know, somebody has upgraded one of your machines. And now it doesn't work anymore, right? This basically lets you make sure you have your own copy of everything that you're building on, so that at any point in time, you can go back and replicate it. I also find this is a really good structure for those who want to share their code, because then they know exactly what version you were using. If you don't do this, you will, of course, get whatever library you're linked against. And when that changes, your code may not work anymore. Even you might not remember what it was. So it's good to sort of do this for code you're going to try and build on top of. So when dealing with this as a submodule, I actually break its program into two pieces. So if I clone my main repo, that's the way I would normally clone something. I can then do git submodule init. This creates a submodule. The correct version is set by the original repository. So this requires that you have access to go get the thing. So if you're working in an offline network or secure environment, that may be problematic. But so the git init submodule init is sort of like a sub checkout. Go check out the correct version of that stuff. You just don't have to know what it is. When I do git clone, I have to know the exact name of the repo. When I do git submodule init, I don't. The repo knew what the version was, so it'll go out and get that. So importantly, inside the submodules, you do not get to have a new branch. Any commits you work on that code is lost in terms of your commits. Now you can still get you can do a git pull and git submodule update to make some of these changes. But the whole point of this submodule is this is not my code. It's just code I depend on. If I'm going to edit it a lot, then it shouldn't be a submodule. It should just be a directory in my repo. So there's a distinction between them. That's the whole reason for that. So Git Clone, which I used a couple times, right, to replicate repositories. So basically on the command line in Linux, or Unix, I can, Bash Shell and new versions of Windows, I can say Git Clone and a URL. Right? That's one way. So Git supports lots of different ways of dealing with it. So I can have a Git protocol. So Git Clone, Git colon / and some URL. I can also have HTTP, so I can say Git clone HTTP colon //. So if the Git server is set up that way, then I can just put a regular web URL in here. I can also access stuff through SSH. This is useful if I'm trying to clone something that's on a server that I have to SSH to get into. Because we use all my SSH keys and whatever to do that. And then I can have a local file system. So any one of those will allow me to access things in different ways. The first two, local file system and SSH, require virtually nothing on the person who's going to let you have the repo to access it. I don't run any specialized servers for the local file system. And SSH, if I have SSH running, I don't have to do anything else. If I want to do it through HTTP or a Git protocol, then obviously they have to run on a web server, if it's HTTP, or a Git server if it's a Git protocol. So to get the changes, the standard process is either get fetch, which goes and gets and downloads all the changes, but does not merge them with my code, or get pull, which both fetches and merges. So if you know there's going to be some conflicts and you want to deal with it piece by piece, file by file, you can just do a get fetch, and then you can merge them file by file. Or I can do a get pull, which is what most people just do. They just do a whole pull. That will both fetch and merge all the files, and then complain if there are conflicts. And then you also fix it. And then I can commit after I'm done. I can do git commit. If there are any changes, I have to do a commit, because when I want to propagate my changes, I want to push them up to the main repo. I have to do git push, and it'll yell saying something like, you know, uncommitted changes or whatever if I try and push something and I don't have all my changes committed. So briefly going to talk about the different protocols. So pros and cons of a local file system. So pros, it's simple. It supports existing access control, and it's NFS enabled, so I can like use a local file system and make a copy on another machine. If you are working on your thesis on your personal laptop, or you have one, I implore you, do something with Git to have a copy of everything you do on some other machine. Having had a PhD student whose apartment was broken into and his laptop with all of his code and thesis documents stolen, right, and takes another year to graduate. That is not a place you want to be. Right? So it's not really hard. So local file system with NFS, right, you could literally just keep having 2 copies for all your code, all your thesis in a repo, and then just have another version someplace else, on GitHub or somewhere on your network file system. To do this, you have to set up some public shares, and it's sort of slow on top of NFS, but it gets you someplace. If you don't want to have your code on somebody else's server, this gives you a complete way of doing it. If you have SSH, the problem with the advantages are you can basically support authenticated access, so no one you don't want to get to it can get to it. It's easy to set up, as most systems provide SSH toolsets, and it's fast. The compression happens before transfer, so it is only sending the deltas that it needs to. The disadvantage of this is you can't have anonymous read access. Right? Everyone's got an SSH in, and you should never have anonymous SSH in, so you can't get it. Setting up an actual Git protocol, it's the fastest. It can actually allow for public anonymous read access. The disadvantage is it doesn't really have good authentication. It's annoying to get it set up, and it uses port 4918, which a lot of places block because it's a non-standard port. So if I try to run this at home, I couldn't do it with this because Comcast blocks 98 because it says that's you're using it as a server, and I'm not allowed to have servers in my personal address, business account there. So it would block that, and I wouldn't be able to access it. But oddly enough, they still let me do SSH. So I can get that to work. HTTPS is very easy to set up. Basically, it's a local file plus Apache. You set it up and point it out, and it's pretty easy to do. Because it's HTTPS, it's very unlikely to be blocked, except by those people that block you because you know how to run a web server. It's the least efficient, but probably the most widely used because it's so easy to set up and easy to do. So when you're working with a remote, on a one-person project, a local repo is enough, except for the fact that your laptop might be stolen, so you should have a non-local local. But if you do it through NSF, then it seems local to you. And you really don't have to bother with remote. So with a small team, SSH write access for a few core developers, get public read access for other people. It's very straightforward to use. So now we're going to start talking about remote repositories and a way of looking at it. So if I want to create something remotely, or I want to create a file, so I can use the command git remote add origin and then some path, right? This is basically saying that Git is supposed to add to the branch called origin, which is the default branch, on the remote server at this address, right? What I'm going to ask it to do, right? And then I can, so if I think of my branches, right, I can think about here's the branch I'm at, and then here's the default branch at our company. So when I clone something, so here's what's living in the Git repo. When I clone it, I get a copy where I have, for this head here, this branch, I have a local branch and a remote branch. If I start making changes, right, my computer will get up to some new set of branches. Well, if there's somebody on the other side, right, this F25 has now been advanced by somebody else. Somebody else on the software team you're working on has pushed 2 new changes. So when I want to work with those, I can work with branches that are different between the local and the remote, right? So notice here, I sort of had a head here and a head here. And now, how do I name them? Well, that's where that origin comes from, right? So if I go and look at this, I can fetch from origin, this command right here, right? And it's basically going to take this updated tree and bring it down. Right? And now I'm down here on the branch called master. And this branch is actually called origin/master because it came from the origin, from the original source. So even though the names look here like they were the same, this actually has a different name. This is origin/master from my point of view. And mine does not have a name that can be seen from there, right? So when I clone, think of that as the root of a tree, and I'm making my own copy. I can see the root, but the root can't see me. I have to push stuff to get the root to see anything. So after I've done this, I can try and pull and merge to put all the branches together. And then if I want, I can push it back up. And if I push it, then these two branches effectively become merged, and there will be one new master that's both of these at the same time. So I already went through this. So Git Clone in the first repo, that copies a repo down. Changes are put back with a Git push. Pushing changes will not change the working copy on the repository being worked on, right? So when I go to do this push, I'm not making any changes locally. Push is all about taking my stuff and putting it on that other server. Branches can be based off of remote branches. So I can say git branch, I'm going to say -- track, that's going to keep this in sync with the other side. New branch, remote/branch. So we talked before about I can easily make a branch, but I really want to say what's the basis for my branch. If I don't say anything after the word branch, so if I just said track new branch, then it would be like, okay, you want a new branch, I'll give you something called new branch. This says this branch is associated with this remote branch. And so keep those two together. So not only can I branch from anywhere in my local tree, I can branch from something in somebody else's tree with this command. So remote configuration file is stored in git config. So you can actually have multiple remote backends. So when I go to do the command git clone first repo, right, I can actually also, through this branch command, add other locations. In fact, this is part of what makes it potentially very distributed. I can have in my git config the same repo that could come from 2 or 3 places. So if one server is down, I can go get it from the other and still keep them in sync. As long as I'm using named remote branches, I can do a whole bunch of stuff with that. So for software versioning, Git is very powerful. So create the convention, the server. You work from the centralized server. There's lots of tools for transmitting the things, right? And it's being used for the core development of things like Linux, Ruby on Rails, GitHub's code is all on GitHub. And there's a ton of things on GitHub for you to go look at. So tons of software versioning. That's really what it was initially designed for. But it's been developed for some, is that a question or? No, okay, yeah, I understand. If you know Git, this is one. So beyond software versioning, what else can I do with Git? What else might I do with Git besides keeping versions of my software? Storage. What do you mean by storage? Yeah, so in fact, you can literally use it for backups. Right, so you can basically have a bunch of data experiments, right? They're not code, but I have all these things, right? You can store them by GitHub by having a repo, regularly local commands update my stuff, regularly push the backup location, right? And you get a simple version of this, right? So if I have data sets, I can maintain them all on GitHub. Makes it easy to share. It makes it easy to make changes and push and copy, but also then have an offsite backup because you're not on my thing. There's a limit. So if you, I'll tell you, if you start putting like a terabyte on GitHub, they're coming after you. If you accidentally add a terabyte to GitHub, they come and yell at you. Your account, your free accounts aren't free of a terabyte. But companies will still pay for that. But for you, it's a great way of just saying, okay, I've got all my data sets and whatever, right? Especially if you do any work to sort them and put them in the right file format and directory structure, whatever for your code. They're not code, but they should be in Git, and they should be backed up. Okay. How about anything else? Can you think of anything else? These are now a little bit, the next one's a little bit more production oriented. So imagine that I actually have lots of Apache environments, right, where I'm working on websites. It's a kind of software development, but a lot of it is not code, right? It's like text files and images and all this other random stuff. So you can do Apache environment with multiple environments. So I can literally take my environment, clone it on a dev machine, do some development, test it out, push all the changes, go over to the production machine, and pull it back out of Git, and now I have an updated version of it. Right? Minor differences between the environment, things like IP and log levels, whatever, all those are maintained in files that are not in Git, but all the production, all the other files go with it. So this is a great way for you to manage different experiment code versions, right? Data that are used process, right? You make different subdirectories, you make different Git branches, and then you can easily switch back and forth between them. Much more efficient and much more reliable than commenting code in and out, which I still see lots of PhD students like, I will try this in Python. Right? So in Python, right, I will just like comment out 3 lines and change these 3 lines, right? Get in the habit, instead of doing that, delete the old 3 lines, add the new lines, make a new branch, commit them with comments so you know what's going on. Because I guarantee you, after a couple of months, it'll be like, I don't know which of these lines I have to uncomment to make this work. You want to have control over your code. And then lastly, which will be related to where we're going, Git is actually really good for documents. It's really well matched to LaTeX. LaTeX, because it's really a text file, right, not like a Word document, right, fits very well. It's very efficient with Git. I find in the process within my lab, we do most of our shared papers using 1 sentence per line. And that has to do with the fact that Git does merges by lines. Right? So it'll take line of this file, line of that file, look for the differences and decide if they conflict. So if I have 1 paragraph as 1 line, right, then when I have that, I edit this, 2 people editing the same paragraph all conflict. That's always a problem because not more merging. If I break my sentence up into 3 lines, then I won't have these merge conflicts, but what might happen is somebody edits the first part of the sentence, and somebody else edits the last part of the sentence. They get a broken sentence because I've now grammatically messed stuff up. So most the text editors like Emacs, Vim, gedit, many of them have a 1 sentence per line mode where they will try and put 1 sentence on every line and they've got paragraphs in order. And if not, you can still just have that as a link. So it's well matched for multi-person editing. The editors, authors, clone stuff from the central server, do a lot of work with it. And to talk about its power, so Overleaf acquired another company called PureLaTeX. Both of them were based, and Overleaf still is. It's actually everything you do in that source is based on Git. There's a repo underlying everything you do on Overleaf that shows you where the files are going. So, and I'll actually go and show you some of that in a second, but because I'm streaming this, I don't know how this recording will be when I change stuff. I will finish up and we'll talk about the assignment, and then I'll go show you some stuff in Overleaf. So one of 2 parts of your assignment for next week. This is a Git. I will update these slides, and I will have to do something because there should have been a repo name there, which means I saved the wrong version of my file. Unfortunately, it's not in Git, so I'll give you a repo. I'll post that in the assignment online as well. Basically, there's a repo I want you to check out. It is a simple LaTeX repo that has currently 1 file in it. Each of you are going to make a new LaTeX file named after your last name. In that file, you're going to take some of the information from your first assignment about yourself, including the photo and whatever. And you're going to add your new file, or whatever you need, into the repo. You're going to update the file, which is assignment 3, that text file, to include your file. So you have to use LaTeX include command, and make sure it all LaTeX properly. Okay, and then you can push all those changes back up to the repo. After at least 2 other people have uploaded their files, so you can't do all this assignment in one sitting because you have to have other people do stuff. You're going to edit one of their files. So Heather's going to edit. Amy. Like, I know it's an American name. You don't. It's like it's not very short from your name, so I struggle. So Heather might edit Amy's file, right? And then you're going to ask Amy a question based on what she wrote, right? And now you're going to push that back up. So you're going to edit her file. The part of this is to get you used to seeing what happens when you deal with Git with files that other people created and edit and dealing with stuff. So you're going to ask at least 2 other people questions, and nobody can ask more than 2 questions. If you go to a file, say, there you got 2 questions, find another person to go ask questions. Should work out. There's enough of you that 2 works out for everybody. When somebody asks you a question, then you're going to go update your file to answer them. Okay? And then if anywhere along the way there are merge conflicts, deal with them. Because you need to get merge conflicts. Who knows? I might edit files in addition to you. I might just go ahead and edit stuff just to mess with you. If there are more than 2 questions in your file, revert it back to a point where there were only 2. So if you look at your file, all of a sudden there are 3 questions, then make it go back to having only 2. Okay? Any questions about this? It's actually relatively straightforward. It's not much time. It's mostly you have to make sure you get the Git commands to push and pull and make all this stuff work. So now let's see how I can. That's not what I wanted to do. I wanted to share this. Okay, didn't want to do that. No idea if it's going to work for recording. We'll find out. Okay, so this is actually the URL, and I'll set the repo so you can see it. So I wanted to show you a few things about Git and dealing with overleaf. So if I go up to my overleaf menu, you'll actually notice over here there's a couple places where I can sync this and copy my overleaf to different places. One of which is Dropbox, the other is Git, and the last is GitHub. So if I just click on Git, it'll actually give me a URL, which is the Git repo for this directory. This is nice because basically anybody you send this URL to will be given read-write access, so you can like share your directory with somebody, but not give them the full overview. They only get Git repo access. And then I can also share it to GitHub. This is what I did with this one. So that's the URL, right? And now this is important. Overleaf, the first one where I just said Git, that is the local Git repo. So every time I make changes in Overleaf, those show up. Here, I actually have to push Overleaf changes to GitHub. So this really is the GitHub version is cloned from Overleaf. And it only gets synced when I push stuff to it. And I can say push these changes. It's going to tell me that there's no new changes, but that's okay. I can commit them, put in comments, whatever. So in doing this assignment, I want you to actually not use the GitHub sync feature of Overleaf. To do your edits, I want you to use local files and whatever, because I want you to have new files, whatever. So, and we will talk about that, but you might have already figured out. But if I want to add a new file in Overleaf, I get to do this upload function, right? I don't want you using the Overleaf. And I guarantee you, I can tell from the logs if you do or don't. So do them by using the Git command line commands in whatever OS you're working on. Git packages for Mac, for Windows, right? So you can do Git on any one of these. We want you to go through using your local tools, not using Overleaf. I will tell you it's an Overleaf because later on it may be easy for you to do it. But mostly in my lab, when we do it with Overleaf, we always just do this. We export it to either Git or to GitHub, right? And then we do work on our thing. But one of the reasons for that is some of our people don't like to have to edit online. I edit papers from students, half the time I'm in the car driving in areas where there are no cell phone service. Driving up the mountain, right? So I want it on local repo that I can work on. You might find it useful for working on a plane or something else, right? So I wanted to make sure you know about this, but for this assignment, do it with Git as a command. Any questions? We'll take a quick break. I'll be back by 3 o'clock, and we will pick up from there. Jennifer, are you there? Whether your journal shows really good. You know, like some of the students are, I give everybody like high grades, 5, but showing good insights into what's going on. Are you focusing just on IRB stuff though? That's what, yeah.
They're using I like Aaron. I got a proposal. Well, we're supposed to be doing adversarial machine learning, but this is the data set published. 2 papers at the very least. Essentially,
Yeah.
the other part is work. Actual hackers. All that. Area of IRB because is doing very, very broadly stuff. Not really anybody.
You have to explain to me why. So the issue is, for IRB, you only have to have it done before you collect anything.
Collected it. IRB didn't go through. But
Okay.
and we still have the are considered a.
We were able to get 2 of our research protocols, so if they're employees of Cisco. Universities. We were able to get, so like our mechanical work workers, in the beginning IRB kept saying every time we use mechanical work is IRB. We eventually got them to recognize that we are paying people to answer extremely simple questions as long as we stick to this range of questions, like just a matter of when they integrate. We're not asking them anything about themselves, we're asking them about the external world and their perceptions of it, right? Not their personal perceptions, but like object facts. Is it a man or a woman? Not how do you feel about men?
Yeah, like it doesn't actually affect that population at all, but.
Well, so but we were able to get a whole bunch of our classified as exempt. If you get the protocol defined as exempt, you might actually be able to use your old data. Because once it's been exempted, you're saying this. So the whole point of exempt is it really isn't IRB, but only the IRB can say it isn't IRB. Well, once you've got them to say that, then it's like, okay, then everything in this category is exempt. Right? Well, I mean, someone's got to do the analysis to figure out, is that actually a risk?
It's worthwhile. Really do what they're doing. I understand why they're doing it.
Okay, so Jennifer says she's not going to the community.